Hi, folks. Welcome back. I hope you enjoyed the food. So we are beginning our afternoon session today. The first talk will be by Dr. Donglai Dai and Kyle Schaefer, who work for X-Scale Solutions. Dr. Dai is a chief engineer at X-Scale and leads the company's R&D efforts. He is an industry veteran, worked for Intel for like over a dozen years, then was a VP for like a startup company in China. So he has a wealth of experience to bring to the field. Kyle is a software engineer at X-Scale Solutions. His work currently focuses on the DPU project. And Dr. Dai and Kyle will be talking about how you can accelerate HPC and AI applications using the various products developed by X-Scale Solutions like MVAPICH2-DPU, X-ScaleHPL-DPU, X-ScaleAI-DPU, and there'll be a bunch of live demos. So without further ado, let me hand over the stage to Dr. Dai, and let's welcome the speaker.
Thank you, Harry. Hi, my name is Donglai Dai, as Dr. Hari has introduced. I'm the chief engineer for the X-Scale company. And since we are a startup, so I'll spend a few, should I use this? Thank you. Okay, so we are a startup, so I'll spend a few minutes to give a brief introduction of our company. So this company started in more than 5 years ago, okay, about 5 years ago. And we basically providing innovative and efficient end-to-end solutions, especially focusing on middleware, communication middleware, okay. And we are providing commercial support as well as services, and also providing trainings for using this. And we emphasize our solutions are platform optimized as well as application optimized. It means doing a lot of tuning based on the customer needs. And we also offer advice for best practices, okay? And so we are actually a vendor, we actually are winners of a few DOE, Department of Energy Small Business Grant. And we actually are a member of open independent software member. It's actually silver level, okay, for open power architecture or consortium. And currently we are offering 5 different products, and I just listed here that we're providing basically MPI library, as well as some specific AI-related platforms. And here we actually, as you can see, we also specialized to use DPU, like what Rich just spoke briefly before us, to use the DPU to do the acceleration for applications. And we are going to demo 3 of this product in the later half of this talk, this tutorial. And we will show specific result as well as the detailed steps to go through to get that, okay. And another reminder is we will have a presentation on Wednesday at 3 o'clock to give more result on the performance. And as one of the most popular middleware for communications, and we're looking at what is the next generation's requirement to get performance out of it. It's first, as we know, we require scalability, and that means high bandwidth, low latency, as well as stable user interface, okay? And as to achieve this, we actually try to leverage non-blocking collectives as well as the point-to-point, but we're going to focus on non-blocking collectives. By non-blocking collectives means when user try to use the collectives, they give some indication early on to allow us to overlap the computation with communication and still keep the semantics correct so that you can check the completion at a later stage when you actually need the data or the resource, okay? And so this is what we will show the result based on this approach. The similar approach can be applied to blocking collectives as well, but as Rich implied early on today, that one may not provide the most opportunities possible. Okay, so using non-blocking will give us more opportunities for overlapping and optimization as far as application is concerned. And here is a high-level overview of what the DPU. We actually use the NVIDIA's Bluefield as our driver examples, okay? And at a high level, basically, this DPU integrate the general programming capabilities through the ARM core with the network interface, basically connected X series. And we are actually we started actually early on with the first generation of Bluefield. But now we already, the latest one we're using is Bluefield 3. But we're going to show the effect of Bluefield, either Bluefield 2 or Bluefield 3 as in our product, because our product can support both. And some of the features, system features are listed here. And since Rich gone through this earlier, so I will not elaborate any more on that. But at a higher level, as you can see, so the thing is, we use this Bluefield in a separate node mode, okay? So we're actually doing the programming on the ARM core to achieve overlapping for communication. And this is the first of the three products I'm going to discuss as well as demo a little bit, give a little bit more details. So the latest release is just May this year, a few months back. And it's based on the open source MVAPICH2.3.7, which also a few months back. Yeah. And it supports all the features available in that open source MVAPICH 2.3.7. And it's actually use a novel framework to do the offloading specifically for non-blocking collectives. So overlap that to offloading that part to DPU. It's actually on the host side we do something, but most of the work is done on the DPU side. And thus, we currently, the library, this version of the library, doing this for I/O2O as well as broadcast, non-blocking. And this is just showing the capability, why we're getting the benefit. It's actually achieving, it's able to achieving about up to 100% overlap between communication and computation. We show this through, we validate this through micro benchmark, OSU micro benchmark, okay? And some of that we'll show during our demo, the data you can see. And this actually can accelerate applications that use or is dominated in their communication by either I/O2O or IBcast, even if it's mixed with other communication library calls. Okay, because a lot of communication, it's not only one or particular one, but it's dominated by certain type of communications. And this is just one example from an application perspective, because no matter what you do, from the end user perspective, does it help my application? Okay. Of course, it's given the resource and time available. And this is showing, we'll show more details later on in the demo live, okay? But this is just one summary to show the result. As you can see here, it's a P3D FFT. Someone here will give a different version to discuss in the next day or two. And this is another version of a popular one. And FFT is quite popular in a lot of different fields to use that as a compute kernel. And this is doing a 3D dimension, 3 dimensions FFT. As you can see, this is input data size. So it's X, Y, Z. Okay. Each of them is a double precision. And so this is the size of the problem. Okay. Given different sizes, this is running on 32 nodes and with 32 ppms per cycle. 32 ppms per node. So it's 100. Oh, sorry. Yeah. Yeah. Okay. It's 32 nodes and 32 ppm, so it's a 1K. Decent size of the parallel programs. Okay. As you can see with this, this is also meaningful input data sizes. And you can see the improvement margin is around 24 for certain applications sizes. Of course, this may change based on your compute as well as your problem sizes, but the benefit actually depends on your computation to communication ratio to show that benefit. But once you get to the communication part, we significantly improve that. We can show that at the micro benchmark level. It's actually quite a significant improvement. Okay, so that is for this. Yeah, okay. And this is a second package, which actually is a restructured or co-designed HPL benchmark. HPL, as you guys all know, that it is the benchmark used to rank top 500 systems in the whole world. Okay, and we're showing this, just show that for this application, even for this application, we are able to improve their performance. I will show you a slide later and see it's quite interesting what exactly we have achieved. And this, I will just show this version of the HPL is the latest one available. And the package we release is co-designed with the latest release from the MVAPICH2-DPU library. Okay, and this particular package, because it's a restructured co-designed code for the benchmark itself. So it supports 2 modes here. One is with the DPU, the other one is without DPU. Apparently, without DPU, you are not doing the offloading. With DPU, you are doing the uploading. Okay, we're going to show you the performance impact. And this particular one uses IBcast, non-blocking broadcast. Should I click here? Okay. And this is, again, this is input size. Okay, problem sizes. And this is 8 AMD processors, AMD nodes, sorry. Each of the nodes has 128 threads or cores on it. So this is half K ranks running. So it's a decent size. Okay. And we have, for each of these sizes, we're showing 4 bars. And I'll explain. This one is using Intel library, purple one. And this one is using HPCX, available from NVIDIA. Okay. And this one is using the non-offloaded version, basically without the DPU. Okay, but it's MVAPICH2 library. Okay, and this red one, the last one, is with DPU offloading. As you can see, first, these 3 bars on the left, remember all these 3 bars are not using offload. So from resource perspective, they are compatible, okay? As you can see, for all of these cases, MVAPICH2 performed the best. Okay, now when you turn on the DPU offloading, as you can see, even for the best, we can still improve on top of it. And one questions someone asked me before, because this is a benchmark used for supercomputers, right? And people using this to achieving the best they can. And people in the past, this application is computation dominated. As you go to peak, the communication portion becomes smaller and smaller. As you can see, as this input grade keep increasing, we see smaller margin and margin. But I'm going to say it another way. In typical system load for all the existing computing system in the world, most time you use the system to do simulations, to try something out. Okay, either you're not using the high peak, or you're waiting for the turnaround. And so this actually becomes more typical for your regular run. Okay, and as you can see, this kind of thing for typical runs, then this bandwidth, the benefit for this library with the DPU offloading is actually even higher than you only run it on the full capacity at the peak. Okay, so last product I'm going to discuss a little bit is a package we did for the AI platform. Specifically, we're talking about for deep learning using PyTorch. As you know that PyTorch as a general purpose platform, a lot of deep learning application is built on top of that. And this package basically doing optimization for the communication occurring. This is, of course, for distributed parallel execution of your application using that PyTorch platform, okay? And then anything built on top of that will be able to get the benefit based on this. And this particular release is built on, again, it's released in May this year. It's built on PyTorch specific versions, which is the most available, the latest available at the time. Okay. Of course, as you guys all know, that deep learning related stuff get upgraded all the time. Okay. So anything up to this point, you can use this library to this package to help you. And so we're going to show you some of the results, but as a summary, we can see some of the tests we're showing that you can speed up your overall execution by up to 17%. Of course, again, this depends on your problem sizes, system configurations, as well as internals of your applications, but this shows the potential. Oh, sorry. Okay. And the system we did this test is description is on the left side. which again is using a system that it's the same as what we're going to demo for you, use for demo, okay? It's actually very similar to what Rich has mentioned earlier this morning. And it's a user system, Intel system with 32 ppms per node, okay? And I think here with up to either 16 or 32 nodes. Okay, so actually this is showing the whole range, starting from 1 node all the way to 32 nodes, and ppm is 32. And as you can see, this is one of the ResNet 20, okay? One of the application actually is popular benchmark for deep learning. And this is using another, the data set of Schaefer 10 data set. And as you can see, as this system scales, we actually get quite stable, sometimes even slightly increased curve for performance improvement, okay? But at least you can see that the benefit is around 16, between 16 and 15, things like that. Of course, this will change based on your system configurations, as well as your problem size itself, okay? But this itself is representative application from the deep learning perspective. Okay. And next, we're going to show live demo. And I have Kyle in the background to help me to go through each steps and showing the result, simulation result, a test result alive, okay. Which one should I switch? Okay, which one to share? Kyle is in which? Oh, that's one. Okay. So we'll start with a micro benchmark to show the first is the IAuto performance. Okay, use OSU micro benchmark. Okay, and we'll show for different message sizes, and we're showing on 16 nodes. This is Intel processor. Okay, 16 nodes. Each node has 32 cores. So this one is 512 ranks, and doing all-to-all communication, non-blocking all-to-all communication among them. And it will show the overlap first, okay? Then overlap is on this side. And this is pure communication time. And this is overall execution time for that benchmark. And since this is a decent size, it takes a little bit time, especially when we reach large message sizes. So this is a message size. So this is a number of bytes. So starting from 64 kilobytes all the way to 512 kilobytes. Yeah. This time somewhere. Kyle? Start, yeah. So Kyle has a start button here to show that, okay. We just explained the setup. He's going to run that real test, start with the start here. Okay, here is the first set. As you can see, that this overlap before, this is where it's the true opportunity. Before we offloading, there is some overlap because the NIC itself is doing something intelligently, okay? But very minimum because of the setup, the application behavior itself, okay? So you can see this is achieving 100%, percentage-wise, close to 100% for all of this. And as you can see, as this package becomes longer and longer, we have less chances for overlapping between communication and computation. Okay. But with this offloading to DPU, we're able to achieve total overlap, or at least statistically total overlap. Okay. And this is the overall execution time for the application. Okay. As you can see, the red one is without the DPU overlap offloading, and the green one is with the DPU offloading. And another thing, this is correlated to what Rich explained earlier today. As you can see, the pure communication time to transfer the same amount of data, the red ones typically are lower, means take less time. The green ones, we do it hard, okay? We spend a lot of effort. It still are slightly higher. So what does that mean? When we're doing the offloading, we actually introduce a little bit overhead to ask the DPU to do the communication for us, okay? But because of this, as long as we structure the code enough, like what Rich was saying, 10% if it's communication, it's reasonable. What we're saying is 50% we even can do that to get the benefit. Of course, give a little bit of room, maybe 40, 60% break, you will see the best results. Okay, now let's looking at the application level to prove our points. We were going to show you the P3D FFT result, which use IOT, or at least this version of the P3D FFT. Okay. Again, we're showing, like I show you in the slides, okay, this is different dimensions, and this is on 16 nodes, 32 ppm, so it's 512 ranks. Is doing this computation. We're going to show from the application perspective, the overall performance impact is what? Remember, one thing is computation to communication ratio play a major role here. But P3D FFT itself is a popular computation kernel, so it has significant meaning to it. As you can see here, for this particular one, 1K cube input on 512 ranks, and this is improvement. It's 21% showing up here. It's hard to read, okay. Then as the input get increased, each dimension increased, actually it's more than just linear, okay, computation itself. And you can see that the overall computation time, that will drop because the scale increases, okay. But you can see it takes a little bit more time each time, and when we increase the size of the input, okay. Okay, so as you can see here, your red actually is much higher, and the green one here. Okay. So again, red one is without the DPU offloading, the green one is with DPU offloading. And this one is showing 20% improvement on the overall execution. And we'll see two more. It'll take a little bit longer. but you will reach a conclusion that this improvement is actually quite persistent. Go ahead, Rich. This is a version that get restructured to use non-blocking auto-all-V. Oh, auto-all, yeah. Not the latest, yeah. Because the latest, they were, I think the owner is changing that to C++ or something like that. Okay, maybe we can look at that and we'll show the impact, yeah. Yeah, we'll show the latest impact. That'd be good. Yeah. Actually, in our previous discussions, he said he even have more opportunities for overlapping or something like that. Yeah, so we were hopeful that we can see even more benefit. Okay. Yes, yes, yeah. So this one is actually 19%. Okay, I did not realize that. Okay, so as the input size increases, you can see the overall execution time get increased. Okay, but the margin actually is quite stable. Then the last one will yet increase. You can suddenly see the scale suddenly get, everything else get shorter. Okay, so as this take a little bit more time, any questions so far? Yeah, go ahead. Yeah. The new version, yeah, Rich, do you know? Thank you for that question. Thank you, Rich, for explaining that. We're looking forward to looking into it to show the benefits. Yeah. Okay. Any other questions? We may have a little bit more time. Hopefully this will be done quickly. But since this is alive, so we have to wait patiently for this. And then I'm going to show the next few. Hopefully it's faster than this, because this is a decent size input. Okay.
Donglai, while we have a moment, we have a question online from Benson.
What's
Benson
the question?
Would you be able to use such benchmarks to aid in cluster procurement, and when is it worth to add DPUs?
Oh, that's a good question. That depends on whether you really pay attention to the faster turnaround time. Okay, and consider the cost. The total system cost is a trade-off. Okay, either you buy a regular NIC without DPU, or you buy a DPU with that. Okay, but for the hardware, it's a one-time investment. Okay, for the benefit is you keep getting this every time you run. So you need to balance that out. Okay, at a certain point, you should see your investment on the hardware really get a return as to your company or your organization's bottom line. You know. Okay, here we go. And this one again, oh, this dropped. Okay, I think what what Samir said in the morning is really, you have to be scared for a live demo. You never know what you're going to get. So we actually run this kind of thing. We get consistent above 17 or 18%. Okay, the margin, performance margin. But this time it doesn't. But still, you can see it's overlapping tick effects. Okay. Okay, next one we're going to. Oh, I don't have slides. Sorry. Yeah, go ahead. Next one, we're going to show the IBcast, the non-blocking broadcast. And we're going to show at the micro benchmark level first. And hopefully this is much faster. Okay. Kyle, go ahead, start. And as you can see, broadcast is what? A single source. Okay, not all-to-all is everybody is trying to send some personalized data to every destination. Okay, and this one is a single source to all the destinations, to all the ranks in your communicator. And we're going to show the effect. Kyle, did you start? He started, okay. And we're going to show the overall execution time and pure communication time. Because the overlap we already see is quite significant. Okay, for this one, sometimes we achieve a little bit lower overlap percentage because the opportunity is less. But we still get to 80% or sometimes even higher. Depends on your system size as well as your message sizes. Okay. Go ahead.
I'm curious, where does your product sit in the message layer? Is it on top of nickel or like an alternative to nickel or?
Oh, we don't use nickel.
Okay.
Yeah, because so we did not use between the GPU.
Oh.
Okay, this is pure between the CPU's communication. Does that make sense?
Well, I understand that you're running one test where you don't use the DPU and the other one where you do.
Yeah, but the whole system does not have GPU.
Okay.
Nickel is for GPU-based communication. By the way, that's a good question. Actually, that's something we're starting to looking at it. Have a system that has a GPU, CPU, as well as DPU. Okay, which actually is showing up in some of the systems I think NVIDIA is working on, as well as superscalers. That one actually superscalers, yeah, like Google or Facebook. That one use IPF. Okay, the IPU, the Intel ones. So it's a system architecture that's that is in the trend for coming. So that's something we start to look into as well. Yeah, but I don't have any available product for that yet. Okay, so this one is quicker. Okay, once it starts. Okay, as you can see here, our margin for improvement is at the micro benchmark level. It's 60, above 60% for this demo. Okay. We actually seen something close to 70 or 80% for some of the tests we did. And for this particular ones, as you can see, again, this one thing is different from the last one. What is that? The DPU actually doing faster. Okay. The reason for that is what? Anyone have a guess? Has a guess? Why does the DPU do it faster? Yeah. From a resource perspective, on the NIC level, yes. Okay. Kyle, next. So next, we're going to show this effect on the micro benchmark level. How does it look on the application level? The application we're going to use is like we discussed in the slides, it's HPL. Okay, which non-blocking after restructuring. The non-blocking broadcast is the dominant communication call, okay, operation. We're going to see, Kyle, did you start? Okay, he gets started. Okay, we're going to see the real application from different sizes, okay, to do this for the test. Okay, what a surprise. Now the green bar is higher. But what has changed? Our measurement changes. Here we show the performance in flops per second. So higher is better. The other one is overall execution time. The lower is better. Okay. So this improves 13% for this particular run. So as you can see, as more different input sizes show up, then you can see the margin is getting changed somewhat. Okay. And in the slides previous I used for the larger size, the computation to communication ratio actually keep increasing. You have less row for communication. Okay, so we expect the benefit margin get smaller and smaller once you reach the real large problem sizes for a given compute grade. Okay, so each rank you have more computation to do because of you increase the overall input problem sizes. Okay, again, this is taking a little bit time because this is something, it's a decent problem sizes for this number of ranks, which is 512. Yeah. And as I show in the slides, so for for this one, without the DPU offloading, without using that, this version of the library is performing the best in the system where we have other MPI libraries available. Okay. Okay, so this one actually showing a slightly larger margin. It's kind of a surprise. But what does that mean is there is some system noise in the background. Okay, but still you can see the improvement is quite persistent. And we have one more size to complete. Okay, so far, go ahead.
Thank you. On the micro benchmark level, so you showed IBcast, the pure communication, and then the pure communication with the MVAPICH2-DPU was
actually improved.
Improved, yes. Unlike the
unlike the dense, yeah.
So can you explain again why we're seeing that?
Okay. one thing is one thing you have to notice is depends on how your design is done. Okay, if you see if single source keeps sending individual messages from itself to the destination, you have one channel to the network. Okay, if you do some clever design, you can see the DPU, how many channels it can have, depends on how many switches you potentially can hook up with. Okay, because that NIC potentially have more channels you can use. But inside there actually has some more overlap as well. Because there is a crossbar integrated on the system, on the DPU. Okay, so there's multiple reasons, but this is something depends on what you try to achieve, you can leverage from.
Hi,
Yeah,
I have a couple of questions. So, so by any chance you have, numbers on Bluefield 3, the newest one?
Yeah. Oh, that's a good question. We did use Bluefield 3, and we see some improvement. But because the thing we're designing, what is good for Bluefield 3? You enhance the floating point capability. You increase the clock speed, okay? But you are still hooked up to the host of the same PCIe bus. So if that becomes the bottleneck, then you will not see significant impact. But since you improved, just a moment, improved the clock speed, whatever you need to do, computation on the Bluefield chip, okay, or the node, you will see that impact. But in our case, we're doing most of the offloading for the constructing the messages. So mostly it's not a floating point of computation. It's integer computation.
So as a result, any operation like O-reduce will not show benefit.
Not significantly, but there is a way you potentially can do that if you're doing some staging design, which you can do better organization, collecting. We can do that. Okay. But for this one, at least in the current design, we have not explored that yet. Go ahead, Rich, you have.
So for things that are non-computational, Bluefield 3 memory bandwidth is about 4x that of Bluefield 2. So if the data is originating from the DPU,
from Bluefield 3, yes,
that you can actually saturate the wire, whereas in Bluefield 2 you couldn't.
Yeah, so that's a staged design through the DPU local memory. Okay, actually Bluefield 2's local memory bandwidth, like you doubled or quadrupled? Yeah, 4 times. Yeah, we actually see something like that when we do some local computations. Okay, but that depends on how that amount of computation, how important that local amount of computation is for your design scheme. Okay, why this takes so long? By the way, so since this is our real benchmark, so take quite some time to do with a decent size, right? Okay. Okay, finally it's here. And this one is showing 17%, like what we say, up to 17%. This actually is demonstrated live. I guess it's a pleasant surprise. Okay, now next one we're going to show, let me see. Kyle, go to the next one. Next one we're going to show X-ScaleAI-DPU. So this is for deep learning related stuff. Okay, start. Okay. So we're going to show the overall execution time of ResNet, like we mentioned before, okay? So we're going to show the scaling on different number of nodes, starting from 4 nodes to 8 nodes to 16 nodes, okay? And for each of this node, I think we're going to use 32 ppm. And again, we're going to show you with or without the offloading. So this is a less number of test results like I showed in the slides, okay? But we're going to show this live. Okay, so this is one we run with, so this is 15%. One we run on 4 nodes. And by the way, for this, the input is the same. So we're seeing what? The either strong scaling or weak scaling effect, okay? Not only on the application itself, but on our performance improvement as well. We'll see the effect. Any reasonable guess what next we'll see? So this is 15%. What did we say? In the slides, we say up or down around 15%, right? So most likely it's about 15% again. Okay, since we have a little bit time, any questions so far? I mean, with regarding to this. And by the way, this is the last set. Thank you for your patience. Okay. And here, oh, this is 17% improvement. I guess we're just lucky today. Okay, can you see another trend? Cut almost half. So this actually is a strong scaling. Okay, so when the next come is what? Somewhere here. Maybe right above 2, line, second line, something like that. Okay, but as you can see, the improved margin is quite sustainable, even with this strong scaling. What does strong scaling challenge us? Strong scaling, you fix the problem sizes, you increase your resource. So what does that result? Each run has less computation. You will have more number of messages to exchange because you have more bodies to help you. Okay, so typically your computation to communication ratio get reduced. And by the way, that's one of the reasons why a lot of applications does not show the nice property of the strong scaling, because communication becomes a bottleneck, okay? And if you can keep scaling like this, maybe we have a nice solution. You know, whatever used to be your challenge for, just a moment, whatever used to be your challenge for the communication bottleneck get alleviated significantly, or at least noticeably by this. Okay, go ahead, you have a question, right?
Yeah, does MVAPICH2-DPU use a cross-global value memory key?
Can you repeat that?
Yeah, in the previous talking,
Yeah.
we know there have the DPU can help the CPU to post the work request via the cross GRIM key, the cross global value memory key. So
Okay.
does the MVAPICH2-DPU use that key.
Oh, keys. You mean exchange them? Oh, okay. Okay. Yeah, actually, what we did, or at least the current design is, we create a process, a proxy, okay, on the DPU side. That's why we use that as a separate mode host, okay, separate host. And, but all this work is transparent from the application perspective, from the end user application perspective. So we're talking about nodes. We never really talk directly about how the DPU itself is working. Okay, the keys for the memory is exchanged at the beginning as part of a setup. Okay, we're going to reuse those keys. Of course, you have to put the effort in to allow that reuse. Okay, but since the key exchange, creating key and exchange key is expensive as well as it has dependencies. All other operations depend on that for performance reasons. So we did it once and we reuse it throughout the entire application run. Of course, that's something we worked out, okay? Now, if some other applications show up that's not necessarily the case, we'll deal with that. Oh, it's all done, right? So as you can see, actually this is, yeah, again, it's a strong scaling. Again, it's a 17%, okay? Okay, I think that's the end of our live demo. And I have 3 minutes left. Any last minute questions? Go ahead.
I apologize if you already covered this. I was in and out. So earlier you were comparing some pure communication of, was it all to all maybe? And the DPU had a higher pure communication time.
Yeah.
So I guess the first part of my question is when we're taking these numbers, the non-DPU numbers are still technically going through the same HCA, right?
Yes.
You're just not using the ARM cores.
That's true.
So is that extra overhead due to simply a DPU process having to be responsible for communication of multiple host processes? Or is it something more fundamental like the DPU cores are simply clocked lower or?
Actually, both of them.
Both.
Yeah, both of them. The amount of work you need to do and your speed to do it. By speed, it means memory bandwidth, network bandwidth, as well as your processor speed. Okay.
Thank you.
And actually, even the PCI bandwidth also is a problem. Okay. It's on the critical path of where the data move. Okay. If no more questions, thank you for your patience, and you're welcome to discuss with us if you have some other questions. And another thing, we'll have a presentation on Wednesday at 3 o'clock. Okay, we're going to go through more performance results than what we show here. Okay, thank you.